Thank you very much. Can you hear me? Yes? I hope so. Okay. I'm very happy to be here, first of all. I'm very happy you are here. I can see that my simple marketing trick with a keyword real money in the title works. It's very good. I want to show you a high-level story about several real-world use cases, applications of data science or maybe data analytics in general in the real-world business problems. But first, a few words about me and SAS Institute. So I work for SAS Institute right now. SAS Institute right now is one of the biggest and oldest company that deals with data analytics. So it was founded more than 40 years ago in the US. More than 25 years we are working in Poland, but in general SAS is a global company. And in fact, most of big companies like top 500 Fortune's list companies, they are our customers. Most of them are our customers. So we can talk about real life applications, I think. And I personally work as a business solutions manager in SAS. So I seek opportunities, new business opportunities, mostly in the field of advanced analytics for telecommunications, banking, manufacturing, energy. So the domain is quite wide. And also a short comment, before SAS, I worked for many years at the university. I did a PhD, then I did a postdoc in the field of artificial intelligence. Then I worked for Samsung R&D, did a lot of interesting stuff with open source, playing with deep learning and so on. So I'm not very focused on SAS technology. I'm more open-minded for open source, for example. Okay, so what is the goal of the presentation? So I've observed that there's a gap between universities and high-tech companies and industry. And by industry, I mean all the companies that are not universities and that are not high-tech companies. So that they are not Google, they are not Facebook, they are not startups. They are just companies which core business is different than IT. So banks, telecoms, but also manufacturing, logistics, and so on. And I'm not the only one who observed this gap. So we heard a nice talk in the morning about that. So there are many reasons, but I'm talking about my perspective and my private, personal, maybe observation. So when I talk to data scientists, my friends, I think that most of them, maybe not all of them, but most of them thinks that industry in general is boring, right? And they are partially right. There are a lot of topics in industry like data preparation, integration, cleaning, explaining with business, with customer what the data means actually. And then it takes most of your time, and then you have I don't know, few days or 2 weeks for modeling. So you use basic models like regression, decision trees, or I don't know. And that's it. So you can say that it's boring from perspective of a person who's a young data scientist, for example. So he prefers to take a Kaggle competition and just do some nice stuff with deep neural networks instead of going to the industry and doing industry projects. And this is also the reason why industry, when we are talking to industry and we are talking about new ideas, new techniques, machine learning techniques, they just don't understand us. They think we are kind of aliens. They have the simple problems. They believe they have some simple data, so they don't get the potential of the new technology. So when we are talking about artificial intelligence, it's like the different world for them. So they don't invest money. They don't invest money in these sophisticated technologies, which makes them even more boring from our perspective. And that's the problem. One of the problems that causes this gap. So what are the possible solutions? First of all, we can show to the industry how these techniques can help them. So that's that's what we do every day almost. So I go to the customers and I try to get data from them and work with the data and show that there are new techniques that give them new opportunities. And on the other hand, I think that it's good to show to the community from time to time that not every project for the industry must be boring. So that's my goal for today. Just present several selected use cases that, in my opinion, from some reason, they are just interesting, can be interesting for us. So let's start with the first case. It's something that we call analytics at the edge. There will be a concrete example, but first, what's this edge? What's this analytics at the edge? So here you can see the basic approach to analytics, or even big data analytics. So the basic approach is that you have some sources of data. You first access the data, store the data somewhere, maybe in Hadoop, maybe in a big, large database, and then you process the data in batch, and then basing on this processing, you generate some output like reports, maybe models that can be used for scoring customers, and so on. But within this case that I'm talking about right now, we have a different type of data and different need. So we are talking about streaming data. So a new type of data appears that is streaming all the time, and it's streaming from, like if you imagine the IoT environment, from millions of sensors. And now the question is, should we really take all the data and store it and then analyze it? So there are at least two reasons why we should do it in another way. One is that if we want to react very quickly, then just this whole process takes too long. And another reason is that maybe if the data is coming continuously from sensors, then it's not a good idea to store all the data and analyze all the data. Maybe it's better to move analytics closer to the source of the data, and then perform some maybe simple or even not so simple analytics there, and just move only the, let's say, interesting part of the data to our storage, and then process it in a more sophisticated way. So this is more or less the approach of edge analytics, so into edge analytics. So we want to move the analytics closer to the source of the data. And this is a sample architecture that I would like to describe. Sorry, that I would like to describe, which implements this idea. Together with Cisco, we've created this architecture. So why it moves here? Okay, I won't use the pointer. Maybe that will help. No, I don't know why it happens. Maybe let's take it like this. We have like two places where analytics can take place, can work, can be executed. One is this edge. So when we have sensors, then probably they will connect to the central data center with some routers. And the key idea here is to put a piece of software, in this case our piece of software, that performs stream analytics. It can filter out some data, it can aggregate data, it can detect simple patterns, but also it can apply some scoring using a trained model, pre-trained model. It can do it directly on the router. So the first level of analytics goes here on the router. Then the data is going to the data center, and in the data center, of course, we have a bigger cluster that can perform some more sophisticated, more complicated analytics. Yeah, and this is, in general, this is a Cisco validated design. So this architecture was tested and validated by Cisco and certified by Cisco. Okay, let me start a short video here. So this is the use case for this application. Imagine that we have tracks. The tracks have sensors on board, tens or even more than 100 of sensors on board. And they are streaming data. And the data is initially analyzed on board, on the track. So some patterns are detected there. Some alerts are generated there. And the data is also transferred to the data center if it is interesting. So let's say that if nothing happens, that it doesn't make sense to transfer all the readings from sensors to the data center because it's costly just to push this data through the network. So if nothing happens, then from time to time we send some information to the data center. But if we detect some events, if we detect some patterns that are interesting, then we change the operation. So first of all, we are sending more data because it's interesting data. We want to store it and analyze it in the future. And second, we generate alerts that can cause some actions. Okay, so the use case. The business context of this use case, it is a leading manufacturer of trucks. I can't tell you which one, but it's one of the biggest world producers of trucks. And the business goal is to reduce warranty costs. The secondary goal is actually to be more competitive with. So the competitors of this truck manufacturer also wants to sell trucks. So this company seeks for new opportunities to reduce costs, to provide better service, to increase the uptime of their trucks, which is crucial for their customers. So transportation firms, transportation companies, for example. The results more or less are here. So we've implemented, we've used our solution using mostly the out-of-the-box functionality with very little of coding here. And we reduced the downtime for trucks by up to 30%. We also created quite nice prediction models that could predict the failures of particular parts in a truck with very high accuracy, even 30 days before the failure occurs. So it's also quite important. And in general, the costs were reduced by 20%. So it's millions of dollars, you can imagine. I will give you some more numbers later about the number of trucks and so on. This is a simple screen. Of course, it's for the visualization of data in the data center. So here you can see data from which can be online in real time, read from trucks. For example, we are monitoring turbo boost and oil temperature. And our system, on-board system, when it detects two peaks correlated with each other at the same time, so that means that the turbo needs to be maintained. It needs to be checked. So the alert is generated, and it's sent to the data center and to the manufacturer, and then it can arrange a maintenance action. Another example. The air temperature is monitored, and the ABS braking system is also monitored here. When we see the wheel slip and we know that the temperature is around 0, then we can generate alert for the driver that conditions are dangerous on the road. And also, which is not implemented yet, we can implement some kind of vehicle-to-vehicle communication to inform other trucks around that there's a problem. So some interesting details. During training, we had training data from a fleet of 40,000 trucks. Each truck was equipped with more than 60 sensors, generating more than 10,000 measurements per vehicle every single day. It was all historical data, so that's where we created some models. These models were then deployed in our component, this one on-board component on the truck, to detect these events, these patterns, interesting patterns, for example. I mentioned that our software was installed on the Cisco router. Oh, sorry for this Polish part. I didn't translate it. Okay, another one. Yes, I was talking about this, so I will not repeat that. The same architecture, the same cooperation between Cisco routers and our software was implemented in another use case for a European energy company. Then ESP our event stream processing engine was monitoring a smart grid, operation of a smart grid. Okay, so that's it about the first case. Second case is a real-time fraud detection in banking. So I will show you the architecture on the next slides, but first I can show you our customer. It's a public reference, so you can go and check some more details on the website. It's a Polish bank, big Polish bank, as you know probably. And this bank implemented a very complete anti-fraud system composed of many components. And I will focus on this component related to the real-time fraud detection. So when we are making some transactions, like in the electronic channels, some transfers, then each transfer is automatically in real time scored by the system. And potentially some of the transfer may be delayed or blocked if a fraud is detected. It's also a nice example of end-to-end and a complete solution, analytical solution for our customers. So in general, we can say that we have two phases when we are working with data for our customers. There's a discovery phase. That's what we like, right? So we can, of course, we need to access the data, but then we can explore the data, model the data. That's the sexy part, let's say. But there's also another part, and this part is easily available using open source solutions. But there's also another part, and we as a SAS are trying to address also this part, which is deployment. So in fact, we not only provide tools to analyze data, but we provide interfaces and tools to implement the results of this analysis. So we provide tools for analysts in bank, fraud analysts in bank, so they can design, test, and simulate so-called fraud scenarios and rules used later to detect frauds. So they can do it in using some visual interfaces. We also provide software to monitor and to analyze alerts. So if the rules deployed here using automatical tools detect some frauds, then we have an interface for analysts to check if this fraud is really a true fraud, or is it a false positive. And of course, we can integrate with banking system and then block transactions and start some procedures related to this fraud, and eventually avoid losing money. So this is more or less how it looks in more in detail. So we have here we have some core banking systems sending transactions in real time. Here we have a first component for stream processing. This is in-memory stream processing, and it takes this transactions data, it combines it in memory with some customer data loaded earlier in a batch mode to memory with a customer profile. Then these transactions go to scoring. They are scored using some rules. I will mention later where these rules come from. And then alerts are generated, and as I mentioned, the transactions may be blocked or passed if nothing is detected. And here we have another important component of the system. So we have historical data store. Also, all the alerts, all the transactions go here and are stored here for future analysis. And we have a system to perform this analysis. So here we have a part of the system to visualize and report the status of the systems, but we also have a component for visual, as I mentioned before, for visual designing and testing and simulating the rules that later can be deployed directly to this operational engine. So analysts work here. They try to detect the rules, simulate them. If they decide that this rule is really a good rule to detect frauds, using our interface, they can deploy it on the fly to the system, which works all the time, for 24 hours a day. Okay, so That's more or less how it looks like inside. And a similar system is realized in, is implemented in the PKO BP bank. And let me come to the last part of examples, telco data, and some problems that we meet with our telecommunications customers. So typical problems solved by telco operators in Poland, and not only in Poland, are things like, maybe you know these names, trend prediction. So we're trying to predict if a customer, mobile customer, a mobile phone owner, will cancel the contract and move to our competitor, for example. Propensity to buy, so standard problem to score offers and prepare best offers, and some other common problems. And there is also a typical approach in telco industry, dated many years before when it was created. So so-called analytical base table is created, and it's basically a long vector of data describing, for example, a customer, and it's created mostly by experts. So we decide what kind of aggregates, what kind of data, what kind of transformed variables are put into this vector. And then this vector is used for prediction. When we add some goal, let's say that the customer will churn next month, we can build this training data and train our models. Usually we also select some features from ABT. We do not use the whole ABT because it's really wide, so it's like thousands of features. We train models, and the problem is that these parts are really done manually. So experts need to decide what vectors put here, what features to choose. So I'll briefly describe a few approaches that we tried to take to solve the problem of these manual actions. So first one is using a deep autoencoder. So we used a deep autoencoder to trim. I don't know if you know anything about it, but I don't have time to explain it. It's basically a neural network that can compress the input vector, which can be our ABT vector, to a smaller representation. In this simple example, we compress this representation to only 10 features. And it's quite effective in this compression. Then we can train a classifier on these features. And when we compare the results to the model created according to the standard procedure, where experts selected 75 features and trained model using similar technique, then using this compressed representation improved the overall results of the prediction model. Of course, we do not use it in an isolated environment. So in fact, we can what we do is we can use it to generate these additional features that are added to the ABT, and then we can use some. I mean, experts can use them, so can choose not only from these features, but also from these highly informative compressed features. Or we can perform some automatic feature selection. And usually, for example, you can use gradient boosting to do that. And usually some of these features are combined with these features, and then the results are better comparing to the standard approach. Another idea that we were considering is to change this ABT concept and to replace this predefined aggregates with some generic aggregates. Like, we are not saying that for each customer we need to aggregate his spendings from the last month and from the last 3 months and from the last half year. But we built some generic aggregates, like daily aggregates, and then we use a deep network to create its own representation basing on the data. So we are giving some micro aggregates, we are giving some target, and the network does the job of building this ABT and building the representation. Time. Okay, that's the last one. The last case is for event sequence discovery. It's quite hot topic recently because we are implementing, for several customers, we are implementing real-time marketing systems where the offers are sent in response to some events. And these events are defined by experts for now. So we say that, let's say I will receive a call from a competitors and I'm close to the end of my contract, so then it is an event, and then automatically I get a SMS or contact from call center. But the problem is that we would like to find out from data what should be the event patterns that we should react to. So we should find these events automatically, or the sequences of events automatically, and then recurrent neural networks can help. So again, I won't go into details, but here instead of building these ABT tables with information about events, we are using recurrent networks that update for each customer. This network can update its internal state, representing the state of this customer. And then training this type of networks with data for all customers, and giving also a training signal. So we are giving a sequence of events and a training signal, 0 or 1, so buy, not buy, churn, not churn. We can achieve a representation which is a really good representation for representing the state of the customer, and that can be used to classify this customer later. So that's it about, if we're talking about the use cases. Few words about our platform. So we are using SAS mostly. And most of these techniques described are available in SAS, particularly in the latest and new SAS analytical engine, SAS Via. So I recommend you to check it out. I'll give you a link in a moment. And what is important, SAS, there was a stereotype that SAS is a closed system. So if you want to use SAS, you need to know SAS language. So here it's completely different approach. So we open up for new technologies. You can easily use our components using Python, Java, R, or web services. So we can use our visual interfaces, our programming language, or your favorite language to use our analytical system. You can also use Python. I will not go into details again, but you can do it if you need. I don't have time, right? So the last information is the link where you can check it out. More information and some trial version that you can test. So 2 things I would like you to remember after this presentation. I hope I convinced you that there are some industry applications that may be quite interesting for us. That's the first thing. And the second one is that you can use SAS with open source technologies together, starting from few months before you can do it.
Okay. Thank you so much.
Thank you.
We have time for a short question.
Sorry if I missed that, but you probably promised us to talk more about scoring in that anti-fraud system, PKO Bank.
More about
scoring. How do you score if the transaction is a fraud or not?
Yeah. So in general, this is a kind of a hybrid approach. It's not that easy to describe it. It's in fact based on rules, expert rules again. So as I mentioned, there is a team of analysts that is analyzing data, including historical frauds, and they are building some rules. And these rules can be enriched with outputs from some predictive models. So you can also train some neural network, for example, to detect a particular type of a fraud. And then you have something like a scorecard when you combine the results of models and these rules into a single score. Right? And this score determines the risk of a fraud.
Okay. Thank you.
It works more or less like that.
Okay, one more.
today it was very interesting, the examples you gave.
Thank you.
What's not very clear to me is if you're a Python user, why would someone use SAS? What's the advantage over the other modules? So what makes it different?
So yes, that's the bigger story of what we can offer to our customers. So I mentioned about that a little bit. So first of all, we have large customers like telcos and bankings with huge teams of analysts that are using our technology. They are using our interfaces, including visual interfaces. So I didn't mention visual interfaces here. We have a lot of visual interfaces to visually explore the data, model the data, and so on. And the second part is the deployment part. So we have like ready solutions that allow you to deploy all the system integrated with, I don't know, bank transaction systems and so on. So in fact, if you are a data scientist and you want to test some new hypothesis, you don't need SAS for that, probably, right? But if you work for a company and you know that later, in order to deploy your model, you will need to integrate with the whole ecosystem, then you can just create this model using your preferred technology. You can use SAS for evaluate models, for deploy models. There are a lot of scenarios.
Okay, thank you.
Okay, thank you so much, Michał, for your talk.
Thank you very much.